Hi, in this tutorial we will solve a question related to radical halogenation. The question asks us, draw the products of radical chlorination and bromination of each compound. For which compounds is a single constitutional isomer formed for both reactions? What must be true about the structure of a reactant for both reactions to form a single product? Let's start from the option A. In option A, we have an alkane, and if you analyze the structure, we have, let's label as A, 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 and we have three primary carbons, and they have three hydrogens each, and at this position we have another carbon, which is a tertiary carbon, and it has a single hydrogen connected. So when we do the chlorination and bromination reaction, let's write the generic reaction. Chlorine in the presence of light, UV light, we are going to end up with two potential products. The first one, the chlorination of the periphery methyl groups, because these all three carbons are equivalent, it's a symmetric molecule, and chlorination of one of them is going to be actually equal to the other ones. So for that reason we are just writing one product, and we are going to chlorinate the tertiary B position. So this is another potential product. So as you remember from the lecture, chlorination is not selective. So basically, if we have different types of hydrogens, all hydrogens can be chlorinated potentially. But statistically, we have one tertiary hydrogen and we have 9 primary hydrogen. Statistically, we expect 1:9 ratio of this product, but the reaction is not very selective. So like we probably we will have more than a 1:9 ratio for this reaction. So that's the first conclusion. Second conclusion, if we do bromination reaction, if we react with bromine, let's erase chlorine. Okay, let's write Br2. And bromination is very selective. Why? Because we have a tertiary position and we have primary positions. Tertiary is going to be much more reactive in the bromination reaction. So potentially the bromine, this product will be the major product. Probably we will have like a minor product of the primary carbon bromination, but this is going to be the major product. Most probably it's going to be almost like 99%. Okay, so that's the first option. And the second option, B, if we do chlorination and bromination, what's going to happen? Again, let's analyze the different hydrogen environments, the different hydrogens, different carbons. So we have here carbon number A, or if we label this carbon A, and we have also the carbons in the aromatic ring. But the aromatic hydrogens are not reactive in bromination and chlorination reactions, in radical chlorination and bromination reaction, because we cannot form a stable radical on aromatic carbons. So for that reason only we have a position, we have a reaction at A. So let's write here, this was for A. For the B, we are going to end up with this chlorination product, and we are going to end up with this bromination product, and we are not going to end up with any constitutional isomers because we have only one reactive carbon for the radical halogenation reactions. Let's look at option C. In option C, we have two different types of carbons. So let's label this one A. And we have also a periphery carbons, all having 3 hydrogens. For carbon A, which is a quaternary carbon, it is surrounded with 4 carbons. We don't have any hydrogen. We will say 0 hydrogen. For the B positions, we have 3 hydrogens. So for that reason, we are going to end up with only one chlorination and one bromination product. So, and also it's a symmetric molecule. All B positions are equivalent, so they are going to be chlorinated or brominated. And if we talk about monochlorination or monobromination product, so this will be the chlorination product, and this will be the bromination product. You can draw anywhere this bromine or chlorine because the carbons are equivalent. Thank you so much for watching the video.